It sits in plain sight, scattered across farmland, grazing country, and expanding towns, quiet, weathered, and easily mistaken for nothing more than ancient hills. Yet beneath this subdued landscape lies a geological system that has not finished its work. The question is not whether mainland Australia has volcanoes, it does. The deeper question is how active they truly are, how recently they have erupted, and how close modern communities now live to the sites of past explosions. Could a future eruption begin without warning in a place that shows no obvious volcanic peak? How would it unfold in a region where no single mountain marks the danger? And if signs were to appear, would they even be recognized in time? Across mainland Australia, volcanic systems do not conform to the classic image seen in countries such as the Philippines or Japan, where towering cones dominate the skyline. Instead, much of the continent's volcanic activity is distributed across what geologists classify as volcanic fields, broad regions that can span tens of thousands of square kilometers, or roughly thousands to tens of thousands of square miles. Within these fields, eruptions occur at isolated points rather than from a single central volcano. Each vent typically forms once, erupts, and then becomes inactive, but the system itself remains capable of producing new vents in entirely different locations over time. This distinction is critical when assessing danger. A dormant cone in one location does not guarantee safety in the surrounding region. Magma can rise through new fractures in the crust, creating fresh eruption sites kilometers or miles away from previous activity. In this sense, the hazard is not tied to a single visible feature, but to an entire region that may appear deceptively stable. Among these regions, one stands out as the most potentially dangerous volcanic system on mainland Australia, the Newer Volcanics Province. Stretching across western Victoria and southeastern South Australia, this province covers approximately 26,000 square kilometres, or about 10,000 square miles. It contains more than 400 identified volcanic vents, making it one of the largest volcanic fields in the world. Its history extends back roughly 4,600,000 years, yet its activity is not confined to the distant past. Eruptions have occurred in geologically recent time frames, with the most recent events estimated to have taken place around 5,000 to 6,000 years ago. In geological terms, that is recent enough to suggest that the system remains active, even if currently quiet. What makes this region particularly significant is not only its size, but its pattern of eruption. Rather than frequent small events, eruptions in this province tend to occur intermittently, with recurrence intervals averaging between approximately 6,500 and 9,000 years. This creates long periods of apparent inactivity, followed by sudden volcanic episodes that can reshape the landscape. The evidence of these eruptions is still visible today. Scattered across the region are cinder cones, lava plains, and large explosion craters known as maars. These maars form when rising magma interacts violently with groundwater, producing highly explosive eruptions that can excavate wide, shallow craters. Some of these features measure over 1 kilometer, or about 0.6 miles in diameter, indicating the scale of past explosive events. One of the most prominent examples is Tower Hill, a large maar structure formed approximately 35,000 years ago. Its formation involved explosive interactions between magma and water, ejecting ash and fragmented rock across the surrounding area. The resulting crater later filled with water, creating a lake that still exists today. Nearby deposits of volcanic ash and pyroclastic material provide clear evidence of the intensity of the eruption. Another notable feature is Mount Gambier, located near the border of South Australia and Victoria. This site includes multiple maar craters, some of which are now filled with striking blue lakes. Geological studies indicate that its most recent eruption occurred within the last several thousand years, placing it firmly within the range of human habitation in Australia. This suggests that early Aboriginal communities may have witnessed volcanic activity in the region, preserving elements of these events in oral traditions. Further east, features such as Mount Napier and Budge Bim illustrate a different eruption style. These sites are associated with lava flows rather than explosive maar formation. At Budge Bim, extensive lava flows spread across the landscape, covering large areas and creating natural channels that were later incorporated into sophisticated aquaculture systems by indigenous communities. These flows extend for several kilometers or a few miles, demonstrating the capacity for lava to travel significant distances from its source. Despite these visible reminders, the region today is home to a substantial population. More than 100,000 people live within areas that have experienced volcanic activity in the last 100,000 years. Towns, agricultural lands, and transportation networks are now established across terrain shaped by past eruptions. This proximity increases the potential impact of any future volcanic event. The hazard is not limited to ground-based effects. Explosive eruptions within the newer volcanics province could generate ash plumes capable of rising several kilometers into the atmosphere or several miles high. Such plumes have the potential to disrupt air traffic across southeastern Australia, including routes connecting major urban centres. Fine volcanic ash can damage aircraft engines and reduce visibility, posing significant risks to aviation. In addition to ashfall, pyroclastic flows represent another possible hazard. These fast-moving currents of hot gas, ash, and volcanic debris can travel at speeds exceeding 100 kilometers per hour or over 60 miles per hour and can extend several kilometers from the eruption site. While the likelihood of such flows depends on the specific eruption style, the presence of maar-forming events in the region indicates that explosive interactions between magma and water are possible. Lava flows, though typically slower, can still pose a serious threat to infrastructure. In past eruptions within the province, lava has travelled distances of several kilometres, covering areas measured in tens to hundreds of square kilometres or several to dozens of square miles. A similar event today could impact roads, farmland, and residential areas, depending on the location of the eruption. The unpredictability of vent location adds another layer of complexity. Because the volcanic field does not have a single central volcano, future eruptions could occur in areas that have not previously experienced activity. This makes it difficult to define exclusion zones or predict precisely where hazards would be concentrated. When comparing this region to other volcanic systems in mainland Australia, its relative level of risk becomes more apparent. In Queensland, volcanic provinces such as the Atherton Volcanic Field and the McBride Basalt Province have also produced eruptions within the last 10,000 years. However, these regions are generally more sparsely populated, and their eruption frequency is lower. Similarly, the Nulla Volcanic Province has produced large lava flows, but with recurrence intervals on the order of tens of thousands of years, reducing the likelihood of near-term activity. By contrast, the newer volcanics province combines several key risk factors: relatively recent eruptions, a large number of potential vent locations, a history of both explosive and effusive activity, and a significant nearby population. This combination places it at the top of mainland Australia's volcanic hazard profile. Yet despite these factors, there are currently no clear signs of imminent volcanic unrest in the region. Monitoring efforts have not detected significant ground deformation, increased seismic activity, or gas emissions that would indicate rising magma. The absence of these signals suggests that, at present, the system remains in a dormant state. However, the long intervals between eruptions complicate this assessment. In volcanic systems, with recurrence intervals measured in thousands of years, periods of apparent inactivity can persist far longer than human observational records. Modern monitoring techniques have only been in place for a fraction of the time between past eruptions. This means that the absence of activity in recent decades does not necessarily reflect the long-term behavior of the system. On average, volcanic eruptions on mainland Australia are estimated to occur roughly once every 4,700 to 4,800 years. This low frequency contributes to a perception that volcanic hazards are negligible compared to other natural threats in the country, such as bushfires or flooding. However, low probability does not equate to zero probability, particularly over extended timescales. The geological record demonstrates that eruptions have occurred during periods when humans were present on the continent. This establishes that future eruptions, while unlikely within any given year, remain possible within the broader span of human habitation. In regions like Western Victoria, where the landscape appears stable and agricultural activity dominates, the idea of a future eruption may seem distant. Yet the ground itself tells a different story. Beneath the soil and vegetation lie layers of basalt, ash, and volcanic debris, evidence of past events that unfolded without the benefit of modern monitoring or warning systems. The challenge lies in reconciling this long-term geological perspective with present-day risk management. Without frequent activity, it becomes difficult to maintain awareness or preparedness for a hazard that may not occur for thousands of years. At the same time, the consequences of an eruption in a populated area could be significant, particularly if it begins with little warning. The nature of monogenetic volcanic fields means that early signs of an eruption could be subtle. Small earthquake swarms, minor ground uplift, or localized gas emissions may precede magma reaching the surface. Detecting and interpreting these signals requires continuous monitoring and an understanding of the region's underlying geology. As population growth continues in southeastern Australia, the interface between human activity and volcanic terrain becomes increasingly important. Infrastructure expansion, urban development, and agricultural use all intersect with areas shaped by past eruptions. This overlap does not imply immediate danger, but it does influence the potential impact of any future event. The newer volcanics province remains quiet, its features integrated into the landscape and in many cases repurposed for modern use. Lakes formed in ancient craters attract visitors, fertile volcanic soils support agriculture, and the terrain itself has become part of the region's identity. Yet the same processes that created these features have not been permanently extinguished. In the absence of constant activity, the most revealing question is not when the next eruption will occur, but how it would begin if conditions beneath the newer volcanics province started to shift again. The geological record suggests that eruptions in this region do not emerge from long-lived, clearly defined volcanic centers. Instead, they originate from new points of magma ascent, fresh points appearing across a wide area of land that may have shown no obvious warning in prior centuries. The earliest detectable phase would likely begin deep beneath the surface, at depths of several kilometers or a few miles underground. Here, magma generated within the upper mantle would begin to rise through weaknesses in the crust. This movement is rarely silent. Small, seismic disturbances, earthquakes too small to be felt by most people, would begin to cluster in a localized area. Over days, weeks, or even months, these events could increase in frequency, forming what is known as an earthquake swarm. Such swarms would not resemble the powerful tectonic earthquakes associated with major fault lines. Instead, they would consist of numerous small tremors, often below magnitude 3 or 4, occurring within a confined region. Their significance lies not in their individual strength, but in their pattern. A concentrated series of small earthquakes beneath a previously quiet area can indicate that magma is forcing its way upward, fracturing rock as it rises. As pressure builds, subtle ground deformation may follow. The ground above the rising magma could begin to lift slightly, sometimes only by a few millimeters or centimeters, or fractions of an inch. Modern satellite-based measurement systems are capable of detecting such minute changes, but only if the region is being actively monitored. In a volcanic field where activity is rare, continuous high-resolution monitoring may not always be in place at every possible site. Gas emissions represent another potential early signal. As magma ascends, dissolved gases such as carbon dioxide and sulfur dioxide can escape through small fractures in the ground. These emissions may not be immediately visible, but they can alter soil chemistry or accumulate in low-lying areas. In some cases, vegetation may show signs of stress or dieback due to increased gas concentrations in the soil. If magma continues to rise, it eventually reaches shallow levels within the crust. At this stage, the chance of an eruption increases significantly. The exact nature of the eruption would depend largely on one critical factor: the presence or absence of groundwater. In areas where groundwater is abundant, rising magma can interact explosively with water. This interaction produces rapid steam expansion, fragmenting both the magma and surrounding rock. The result is a phreatomagmatic eruption, one of the most explosive types observed in the geological record of southeastern Australia. Events such as the formation of Tower Hill demonstrate the power of this process. During such an eruption, ash, rock fragments, and volcanic gases are ejected violently into the atmosphere, forming an eruption column that can rise several kilometers or a few miles high. Ash clouds can spread over wide regions, carried by prevailing winds across towns, farmland, and transport corridors. The immediate hazard from such an event would include ballistic projectiles, rocks ejected from the vent that can travel hundreds of meters or several hundred yards. Closer to the source, pyroclastic surges could move rapidly across the ground, following low points in the terrain. These currents, composed of hot gas and fine material, can extend several kilometers or a few miles from the point of eruption. Further from the vent, ashfall becomes the dominant impact. Even a relatively modest eruption could deposit several millimeters to centimeters of ash, fractions of an inch to a few inches, across surrounding regions. While this may seem minor, ash can disrupt daily life in multiple ways. It can contaminate water supplies, damage crops, and interfere with electricity infrastructure. Fine ash particles can also pose respiratory risks, particularly for vulnerable populations. Air travel would be especially sensitive to such an event. Ash clouds drifting into flight paths could force the diversion or cancellation of flights across southeastern Australia. Airports serving major population centres could experience temporary closures, depending on wind direction and ash concentration. Even thin ash layers in the atmosphere can damage jet engines, making aviation authorities highly cautious in such situations. In areas where groundwater is limited, the eruption style could shift toward a more effusive pattern, producing lava flows rather than explosive events. Sites such as Mount Napier and Budge Bim provide evidence of this type of activity. In these cases, magma reaches the surface and flows outward, forming rivers of molten rock that can advance across the landscape. Lava flows in the newer volcanics province have historically traveled distances of several kilometers or a few miles, covering areas measured in tens to hundreds of square kilometers or several to dozens of square miles. Although slower than pyroclastic flows, lava can still overwhelm infrastructure in its path. Roads, fences, pipelines and buildings cannot withstand sustained contact with molten rock, which can reach temperatures exceeding 1,000 degrees Celsius or over 1,800 degrees Fahrenheit. The speed of lava flows varies depending on factors such as slope, viscosity, and eruption rate. In some cases, flows may advance only a few meters per hour or a few yards, allowing time for evacuation. In other instances, particularly on steeper gradients, they can move faster, reducing available reaction time. One of the defining challenges of a volcanic field is the uncertainty surrounding vent location. Unlike a single mountain volcano, where hazard zones can be mapped around a central cone, the newer volcanics province contains hundreds of possible points where an eruption could occur. This means that areas not previously affected by volcanic activity could still be at risk in the future. Modern communities across Western Victoria and southeastern South Australia are built on or near volcanic terrain. Agricultural regions benefit from fertile basaltic soils produced from past eruptions. Towns and transport networks have expanded across these landscapes, often without visible signs of their volcanic origin. This integration of human activity with ancient volcanic features increases the complexity of emergency planning. If a new eruption were to begin near a populated area, the initial response would depend heavily on the detection of early warning signs. Seismic monitoring networks would play a crucial role in identifying earthquake swarms associated with magma movement. Satellite data could reveal ground deformation, while gas sensors might detect changes in atmospheric composition. However, the effectiveness of these systems depends on coverage and speed of analysis. In regions where volcanic activity is rare, the density of monitoring instruments may be lower than in more active regions, such as the Pacific Ring of Fire. This creates a potential gap between the onset of subsurface activity and its recognition as a volcanic threat. If you found this breakdown insightful and want more deep, clear explanations on natural hazards around the world, make sure to share it so more people can understand the science shaping the ground beneath our feet.